My name is Ishan Raucher, and I'll be answering FRQ 2000, number 2. The problem is described as a block of mass m starts at rest at the top of an inclined plane of height h, as shown in the figure above. The block travels down the inclined plane and makes a smooth transition onto a horizontal surface. While traveling on the horizontal surface, the block collides with and attaches to an ideal spring of spring constant K. There is negligible friction between the block and both the inclined plane and the horizontal surface, and the spring has negligible mass. Express all algebraic answers for parts A, B, and C in terms of m, h, k, and physical constants as appropriate. Part AI is described as derive an expression for the speed of the block before it collides with the spring. The initial energy is then equal to the final kinetic energy of the spring, and the only initial energy is the gravitational potential energy. So Ui equals K can be written as mgh is equal to the kinetic final 1/2 multiplied by mv squared. This can all be obtained from the formula sheet. Then solving for v, we can cancel out m on both sides, leaving us with gh equals 1/2 v squared, and then multiplying by 2gh equals v squared, and then taking the square root, v is equal to the square root of 2gh. This is an expression for the speed for part AI. Part AII is described as, is the speed halfway down greater than, less than, or equal to 1/2 the speed at the bottom of the inclined plane? The key to solving this problem is realizing that the square root of height is proportional to speed. We have previously declared that v is equal to the square root of 2gh. So now solving for v2, the new speed at 1/2 the height, we can now plug this in here, so we get v2 equals the square root of 2g 1/2 h. We previously determined that v is equal to the square root of 2gh, so v2 is equal to the square root of 1/2 v. This can be written as v2 equals the square root of 1/2 multiplied by the square root of v, and solving this will give us v2 equals 0.71 v, which is greater than half the speed, 0.5 v. So the answer to this question is greater. Part B is described as derive an expression for the maximum compression of the spring. To solve this problem, we must use the law of conservation of energy. We must set the initial gravitational spring energy equal to the final energy of the spring. Once again, this can be derived from the formula sheet as well. The initial gravitational potential energy is mgh, set this equal to 1/2 multiplied by kx squared. Now we must solve for x, or x max in this situation. To do this, we will multiply by 2 and then divide by constant k to get 2mgh over k equals x squared, and then x max is equal to the square root of 2mgh over k. Part C is described as derive an expression for the time from when the block collides with the spring to when the spring reaches its maximum compression. To solve this problem, we can use the equation for a horizontal spring block oscillator. The period t is equal to 2 pi multiplied by the square root of m over k. Knowing that at 1/4 of the period the spring will reach its maximum compression, we are really solving for t over 4. So t over 4 is equal to 2 pi times the square root of m over k. Multiplying by 4 to the right side, 2 over 4 becomes pi over 2 times the square root of m over k. And the t of the period here is really the time that we're looking for, because this is when the spring will reach its maximum compression. So this equation here is our answer to part C. Di is described as the block is again released from rest at the top of the incline, and when it reaches the horizontal surface, it is moving with speed v0. Now suppose the block experiences a resistive force as it slides on the horizontal surface. The magnitude of the resistive force F is given as a function of speed v by F equals beta v squared, where beta is a positive constant with units of kg/m. So di, write but do not solve a differential equation for the speed of the block on the horizontal surface as a function of time t before it reaches the springs, expressing your answers in terms of the constants that we will be using. So the key to solve this problem is to first notice our forces. The forces in the y direction are not needed for this problem, but the sum of the forces in the x direction is negative beta v squared. And once again, the drag force here is negative because it is acting in the negative direction against the motion of the object. As a result, we have ma equals negative beta v squared, and replacing a with dv dt converts this into a differential equation. So our final answer here will be negative beta v squared equals m multiplied by dv dt. Part D2 is described as using the differential equation from part DI shows that the speed of the block as a function of time t can be written in this form here, where v naught is the speed at t equals 0. So we start with the differential equation from the previous part, negative beta v squared equals m dv over dt. Dividing by m and then dividing by v squared, we now separate the variables to get negative beta over m dt equals 1 over v squared dv. We can now integrate both sides, and now we result in negative beta t over m plus c equals negative 1 over v of t. Now we can use the initial condition given to us. At t equals 0, v of t is equal to v naught, or v sub 0. As a result, solving for c will get us c equals negative 1 over v naught, because plugging in 0 here will just result in 0 plus c equals negative 1 over v sub, or v of 0. As a result, we can plug this back into our equation, negative beta t over m plus negative 1 over v naught equals negative 1 over v of t. Rearranging this, we get 1 over v of t equals 1 over v naught plus beta t over m. The final part asks us to sketch graphs of position x as a function of time t, velocity v, and acceleration a, all as functions of time t, for the block as it is moving on the horizontal surface before it reaches a spring. So we can use the concept of drag force here. The drag force decreases velocity until it will reach a constant terminal speed. As a result, we start with a higher velocity value. It is decreasing, and we are slowly going to approach an asymptote in which we reach our terminal velocity. Using the equation negative beta v squared, we can also illustrate the acceleration. We know that it is in the negative direction, or it is in the opposite axis of the graph due to the negative here. So we can illustrate it as approaching the positive axis, but it is going to be approaching at decreasing values and reaching an asymptote as well. Position is always moving forward at a decreasing rate. So we see an initial higher rate of increase, but then it starts to even out and once again reaches a constant rate.